flip video about Charles' law. Before we can talk about what Charles' law is, let's kind of review about what temperature is. Temperature is a measure of average kinetic energy, and kinetic energy, kind of like the word kinetic wellness, is energy of motion, moving around. So we measure the movement of our molecules, and that gives us temperature. There are three different types of scales for temperature. The first two you're probably very familiar with, and that is degrees Celsius and Fahrenheit. The last one is the new one we're using for this chapter. Gases use Kelvin as their temperature scale. It is the way we are going to measure temperature for our gas unit, Kelvin, the K. Okay, so what is Kelvin? Well, the Kelvin scale, again, is used for all gases, and the Kelvin scale is based off of the absolute temperatures, and therefore we have no negative values. In the degrees Celsius and Fahrenheit, we're given negative temperatures, like outside right now, it's -2. In the Kelvin scale, there is no negative. 0 is the lowest you go, and 0 K for Kelvin is known as absolute zero, which I'm sure you've heard of. 0 Kelvin, if I was to say what is that in degrees Celsius, well, 0 Kelvin is very cold. Again, that is absolute zero. It would register outside as -273 degrees Celsius. Brr, that's cold. All right, so I want all of my temperatures for this unit to be in Kelvin. Therefore, I need a conversion, and this is a very easy one. All I have to do is take 273 and add it to any of my degrees Celsius to get a temperature in Kelvin. So if I had 10 degrees Celsius, 10 degrees Celsius plus 273 would give me 283 Kelvin. So that's all I would have to do. Let's remember that, write that down. All of our temperatures are going to have to be converted. Okay, so now let's actually dive into Charles' law. Charles' law talks about two variables. They are temperature and pressure. Temperature and pressure. So let's take a look here at my beaker full of gas. My beaker full of gas. Okay? And if I heat my beaker full of gas, okay, we're going to put this little plunger, push down this plunger. Here's my volume. And I'm heating up my gas, and it's moving around and moving around and moving around. Okay? Well, what if I decide to increase that heat? So not only do I have heat already going in, I now have more heat, more heat. Well, what starts to happen is the kinetic energy of these gas molecules starts moving around faster, and look what happens to the volume of the gas. It starts to expand. The volume of the gas expands. This is what happens, right, when I start to increase my temperature. Okay, the volume expands. And so in reverse, if I was to decrease my temperature, all my molecules start to move a little bit slower, and the volume starts to decrease. Okay? So if we were to look at this picture here of the two compared, low heat, high heat, low heat, the molecules move a little bit slower, and so there's not as much volume. High heat, molecules are moving faster, pushing up on that plunger, and so giving more volume to spread out. They're hot, they're moving around really fast. It's a lot of kinetic energy. So Charles' law, you'll have to excuse me, I just made a mistake, is not about temperature and pressure. It's about temperature and volume. Let's erase that and write the right thing in. It's about temperature and volume. I don't know what I was thinking. Temperature and volume, not temperature and pressure. Okay, so again, as we just saw, as the temperature increases, ooh, those molecules are moving really fast, pushing up. Expanding, volume increases, and vice versa. If I lower the temperature, the volume goes down. The molecules move slower and go down in volume. This type of relationship, as one thing goes up, the other thing goes up, or vice versa, as one goes down, the other goes down, is called a direct proportion. They move in the same way, direct proportion. Okay? All right, let's take a look at a sample problem. A gas has a volume of 5.30 liters, liters, at 25 degrees Celsius. Uh-oh. We must convert temperature to Kelvin in any of these gas problems. We'll do that in a second. The new volume, what is the new volume when temperature increases to 100 degrees Celsius? All right, well, we're going to be needing a formula for this. So what is the formula? This is it right here. Take a second, write this down, box it in. My initial temperature and volume is equal to my final temperature and volume. So if you notice here, I have initial conditions. I start off with a volume of 5.3 liters. That's my initial volume. And that volume is at this temperature, my initial temperature. And then something happens, a change, and I have a new volume. That's my second one. And I have a new temperature. That's the new one. So the 1 stand for initial, the 2 stand for final. Okay? A good way to organize your information is to make a list of your variables. Again, here we go. V1 was the first volume I was given at the first temperature, T1. V2, I don't know. They asked me, what's the new volume? X. T2, the new temperature is going to be 100 degrees Celsius. So the first thing we have to do is we have to convert our temperatures to Kelvin. So let's do that now. Remember,